An alternating series is exactly that, a series where the terms alternate in sign. They alternate between positive and negative. When we have alternating series, like, let's say, 1 minus 2 plus 3 minus 4 plus 5 minus plus yada yada, or 1 minus a half plus a third minus a fourth, etc. We can use the alternating series test to determine if the series converges. Now, this alternating series test, or the fondly named AST, is a test for convergence and convergence only. We cannot prove divergence with the alternating series test. So remember, we have the sum of some terms an, so altogether this business is an, but we split it into two bits, the alternating part of an, and then un, the non-alternating part. If these un parts follow the following three criteria, then the series converges by the alternating series test. And the criteria is, first, that the uns, the non-alternating part of the series, are all positive. So we want to show that un is greater than or equal to 0 for all n. Secondly, the uns need to eventually be non-increasing. Non-increasing means they're not increasing. It doesn't mean that they strictly have to be decreasing. They could become constant at some point, but we need to prove that somewhere they are no longer increasing anymore. It's sufficient to show that they are decreasing, but it might be that they become a constant. So we say that un needs to be greater than or equal to the next term, un plus 1. So that equal to bit for all n greater than or equal to some particular place n. That equal to part means the eventually non-increasing. Anyway, and then the limit of those terms, the sequence un needs to approach 0. So let's look at this test and see if we can make some decisions. Here's a series that clearly alternates. It's negative 1 to the n plus 1 over n. So the alternating part is this negative 1 to the n. So the un is the non-alternating part, 1 over n. The criteria were that, first, these un terms, 1 over n, needed to be positive. They need to be greater than 0. And that is true for all n, because remember, n starts at 1 and ends at infinity. So there's no way to get negative out of that un. Second thing we need to require is that it's non-increasing. That means 1 over n needs to be greater than or equal to the next term, 1 over n plus 1. So this means that n plus 1 needs to be greater than or equal to n. Therefore, 1 needs to be greater than or equal to 0 for this to be non-increasing. This thing is true. That's true all the time. And lastly, we just have to show, number 3, that the limit of these terms approaches 0 as n approaches infinity. Well, the uns approach 0, and that really does happen. So we can say, therefore, the series converges by the alternating series test. Pretty nice little test to run, just those three criteria, and then we say it converges. Let's see another example. Now we have negative 1 to the n times n squared plus 5 over n squared plus 4. So the un, the non-alternating parts of this series, are n squared plus 5 over n squared plus 4. And the series is alternating, so let's try the alternating series test. First, are the uns positive? N squared plus 5 over n squared plus 4. These are always positive numbers over always positive numbers. Surely that has to be greater than 0 for all n. Number 2. Are these terms eventually non-increasing is n squared plus 5 over n squared plus 4 greater than or equal to n plus 1 squared plus 5 over n plus 1 squared plus 4. This one becomes quite a bit of algebra. If we cross multiply, we'd have n squared plus 5 times n plus 1 squared plus 4 greater than or equal to n squared plus 4 times n plus 1 squared plus 5. So if you want to pause the video here and do that algebra, there's some FOIL and then some FOIL again. You can simplify this down to the fact that 2n is greater than or equal to negative 1, and that is true for all n. So we've met the first two criteria for the alternating series test. The third one is just to show that the limit of these terms as n approaches infinity is 0. We have n squared plus 5 over n squared plus 4. Unfortunately, however, this limit is 1, which is not 0. So we cannot use the alternating series test to prove convergence of this series. The alternating series test does not apply. This does not mean that the series diverges. We cannot use alternating series test to prove divergent, but we can use something else. What about that thing that we learned called the nth term test for divergence? So if we look at number 3, 3 says that the limit of these terms is 1, and the nth term test for divergence said that the limit had to be 0 for the series to converge. So we could say that by 3 and the nth term test for divergence this series diverges. Now that we are a little familiar with the alternating series test, let's look at this particular series. We already showed in example 1 that this alternating harmonic series converges by the alternating series test. However, if we were to look at the absolute value of this series, the absolute value of negative 1 to the n plus 1 over n, that's the series 1 over n. That guy is a divergent p-series. So we have a series that converges only when the terms are alternating. That's an example of what we call conditionally convergent. We spoke a little bit about absolute convergence in the previous sections. A series converges absolutely if the series of absolute values converges. However, a series converges conditionally if the series itself converges but the absolute value of the series diverges. So what we do in practice is test first for absolute convergence, and then if it does not converge absolutely, we test for conditional convergence with the alternating series test. So let's see how that looks in practice. The first thing you'll notice about this series is that it's alternating. There's an alternating term there, but before we use the alternating series test, let's simply consider the absolute value. We could check this series for absolute convergence. If it converges absolutely, it will converge with the alternating terms as well. So the absolute value of the series would be the series without the alternating sign, 1 plus n over n squared. Well, that series is the series of 1 over n squared plus 1 over n. Now, 1 over n squared converges, that's a convergent p-series, but 1 over n diverges, and diverges wins in that battle. Divergent plus convergent means divergent. My Cal2 teacher used to say an explosion explodes, so the divergent just kind of explodes all over the convergent p-series. Therefore, the series diverges in absolute value. If it's not absolutely convergent, then we'll check for conditional convergence by the alternating series test. First, those un terms, the non-alternating terms, 1 plus n over n squared, need to be positive. That's true here for all n. Second, we see as long as they're non-increasing, so 1 plus n over n squared needs to be greater than or equal to 1 plus n plus 1, the next term, over n plus 1 squared. Do a little algebra here. We find that n plus 1 cubed is greater than or equal to n cubed plus 2n squared, 2n squared, which simplifies eventually to 1 greater than or equal to 0, which is true for all n again as well. So the third thing we need to do is check that these terms approach 0. The limit as n approaches infinity of the un, 1 plus n over n squared, really is 0. So we can say, therefore, by the alternating series test, the series that diverges in absolute value converges conditionally. It's a conditionally convergent series. Here's a series that may not be clearly alternating until you pause to consider what happens at the cosine of n pi. Cosine of 1 pi is negative 1, cosine of 2 pi is positive 1, 3 pi is negative, 4 pi is positive. So this term is none other than negative 1 to the power n. At 1 pi, negative, at 2 pi, positive. So really the series could be rewritten as the series negative 1 to the n instead of cosine times n cubed. Now that's only because the argument is pi. If it were pi over 2 or if just n, it would be totally different. So we're considering first the absolute value of this series. Consider the series of absolute values of this term. Series of simply 1 over n cubed. Well, 1 over n cubed is a convergent p-series. So since that series converges in absolute value, we would say that this series converges absolutely. And there's no need to try the alternating series test, because if it converges absolutely, it converges conditionally as well. Here's one last example. The negative 2 to the n, we need to separate out what this means. This is the series from 1 to infinity of negative 1 to the n times 2 to the n. So if we consider the absolute value of the series first, check for absolute convergence. The series, absolute value, negative 1 to the n times 2 to the n, is the series of 2 to the n. That series is geometric. Geometric with common ratio r equal to 2, which is greater than 1, therefore this series diverges in absolute value. Since it diverges in absolute value, we need to check the alternating series test to see if the series converges conditionally. So the requirements there, first, the un terms, which are 2 to the n, are greater than 0. Well, absolutely. 2 times 2 times 2, no matter how many times you do it, you'll get positive values. Let's see if these are non-increasing. So we want to show that 2 to the n is greater than or equal to 2 to the n plus 1. Well, that means 2 to the n is greater than or equal to 2 to the n times 2. So if we divide both sides by 2 to the n, that says 1 is greater than or equal to 2. That, my friends, is true never. This is a lie. If that's the case, that this series fails the alternating series test. That doesn't mean it diverges, it just means we cannot prove convergence in the conditional. So we need to find something else that will tell us whether the series diverges or not. How about the nth term test for divergence? We showed that it diverges absolutely, but that's not sufficient for the alternating business. So let's do the nth term test for divergence. The limit, as n approaches infinity, of negative 2 to the power n. The limit here is infinity or negative infinity, right? Kind of depends on whether your infinity is positive or negative in the exponent. The point is that this limit, whatever it is, infinity, negative infinity, or doesn't exist, is not equal to 0. And if the limit's not equal to 0, we can say that the series diverges. So where we stop here would lead us to think, well, gee, why don't I start with that idea? Why don't I start with testing the series for divergence? And if it has an opportunity to converge, then we can check it for absolute convergence in absolute value. And if it doesn't converge absolutely, then we'll do the alternating series test. So we're starting to develop this plan. First, check and see if it even has an opportunity to converge. Test it for divergence with the nth term test. Second, test it for absolute convergence. And third, if it failed absolute convergence, check it for conditional convergence. So that is sort of developing our plan for determining whether series converge conditionally, or diverge. Let's make a summary of these tests. Here are some of the tests that we've used so far. The nth term test should always be your first thing to go to. Number one attempt is take the nth term test. Just see if perhaps it diverges. Remember, if the limit, as n approaches infinity, of the series an, or the terms, the sequence an, is not equal to 0, then we can say that the series an diverges. That should be fast. If it might converge, you would try to recognize it. Perhaps it's a geometric series. The series a times r to the n will converge for common ratios r less than 1 in absolute value. Otherwise, they diverge. And the p series, the sum of 1 over n to some power p, converges for any value of p greater than 1. Otherwise diverges, right? So if we have series with non-negative terms, that means they're already positive, then we could try the integral test. Those things are things that look like you might want to integrate them. Usually things with like natural logs and other spare derivatives of whatever that natural log is, the natural log of n, or maybe you want to integrate anything that looks like it might need by parts, or a trig sub to integrate, u sub, of course. But if something integrable, we could try the integral test. If not the integral test, perhaps we want to compare this. Maybe it looks similar to a known geometric or p-series, so we could use any of the comparison tests. Remember, there were direct comparison test or the limit comparison test. And then if we had something that had factorials or something that looked kind of complicated, we wanted to simplify, we would do that with the ratio test, or anything raised to the power n, we would use the root test. So you have these options. Maybe you find one that's sort of your go-to, and if that doesn't work, you try something else. You remember that there are results of comparison tests and ratio tests that you have to be able to interpret. So those mean that you need to remember the tests. The integral test is kind of easy. Converges or diverges is pretty evident. Now, if a series has some negative terms in it, then we want to consider whether or not it converges absolutely. So we would do that first. If this guy converges, then we know that the series also converges. It converges absolutely. But if it does not converge, if it diverges in absolute value, then we use the alternating series test. The AST here to check for conditional convergence. So again, here's our plan. 1, check the nth term test for divergence. 2, see what we know about it. Run one of these tests. So the geometric or p-series or terms that aren't negative, there's no need to mess with the absolute value of it because they're already positive. But if they do have some negative terms, consider what happens in absolute value. If it converges from any of these, it converges absolutely. And then if it doesn't converge in these, then you have this third step. The final step is to use the alternating series. If it diverged in absolute value and there are these alternating terms, then we check with the alternating series test. So here's one final example of what we would like to do in implementing the process of testing any series. You notice that we have an alternating series, but before we do that, we just want to give a mental check to make sure that the nth term test doesn't fail us. The nth term test says what's the limit of this series. As n approaches infinity, -1 to the n plus 1, that's alternating, 0.1 to the n over n. 0.1 to the n is 1/10 to the n times 1 over n. So what thing will win here? That limit is definitely 0. We have some numbers down here getting bigger and some numbers over here getting bigger, divided by 1. Even though the signs are alternating, the limit is 0. So this series might converge. Now let's investigate that convergence. First, consider the absolute value of the series. So what happens if it's not alternating in sign? Then we have the series of 0.1 to the n over n, which we already said 0.1 to the n is 1 over 10 to the n, and then multiply by 1 over n. So there's kind of a lot going on here. We could compare it to the geometric series and see if that works. So let's do that. The geometric series 1 over 10 to the n, that's a common ratio r of 1/10, which converges. We can use the limit comparison test or the direct comparison. I suppose I would go with direct comparison. Doesn't look like we don't have too many terms here going on, so maybe the direct comparison will not be too tricky. In the direct comparison, we have a convergent geometric series. So since it converges, we want to show that this convergent series, 1 over 10 to the n, is greater than or equal to the series we have, 10 to the n times 1 over n. Or maybe you think of it this way, the series we have, 1 over, let's write it as n times 10 to the n, needs to be less than or equal to our convergent series, 1 over 10 to the n. Those things mean the same thing. I think in class we mostly looked at it this way to show that this guy who was convergent is going to squeeze down the series we have that we don't know what it does. So let's see if this is true for all n. That makes 10 to the n less than or equal to n times 10 to the n. And we divide both sides by 10 to the n, you have 1 less than or equal to n. And that's true for all n, right? N goes from 1 to infinity. Alright then, so we found that this series, 1 over n times 10 to the n, converges, which is the absolute value of the series in question. Therefore, the series in question, negative 1 to the n plus 1 times 0.1 to the n over n, converges absolutely. There are some more examples in the rest of these note outlines. I would like you to look at them, try them yourself, and then compare them to the posted solutions that I'll put up. So it will make more sense to you if you try it a little bit. Remember, there's 3 steps. N-term test, consider the absolute value. If this guy diverges, then you move on to the 3rd step of trying the alternating series test.